Okay, great. Today, we are very honored to have Dr. Petros Drineas from Purdue University give our 1W-MINDS seminar today. Dr. Drineas received his PhD in computer science from Yale University in 2003. Drineas was on the faculty of RPI from 2003 to 2016 and was a visiting researcher at Microsoft, Yahoo Research, and the San Diego National Lab. He is currently a full professor of computer science at Purdue University. Dr. Drineas received a lot of awards. For here, I only mention a few. For example, he received an SF Career Award in 2006, IBM Academic Award in 2021, and recently he was selected as a Science Fellow. And his research interests are mainly focused on the randomized method in numerical linear algebra and applications. Today, he will talk about randomized linear algebra for interior point methods. Okay, it's your turn, Petros.
Thank you very much, and I very much appreciate the kind introduction and, of course, the invitation to the seminar. I'm also fully aware that this is Thursday of finals week in most places, including, I guess, your university and mine, and people are starting to get tired. So I'm going to try to break up the talk in two parts, essentially. The first part is going to talk about randomized linear algebra, and I'm going to give a brief overview of the field, talk a little bit at a high level, hopefully accessible, I hope, to most of the audience. And then in the second part, I'll get to interior point methods and how to use some of the ideas from randomized linear algebra to solve linear programs. Just to make it clear, interior point methods are the technique of choice at this point in theory and in practice to solve large-scale linear programs. I'm not going to go beyond linear programming at all. I'm only going to focus on LPs. So I should also say and acknowledge right now my collaborators in the work for interior point methods. There are many, many people working on randomized linear algebra, but in applying randomized linear algebra to interior point methods, this is joint work with Avron at the University of Tel Aviv. I'm going to go from the bottom up. Palma London, she used to be at Caltech when we started this work. She's now at Cornell. Agniva and Gregory are students of mine. Agniva has graduated. Gregory is still at Purdue. So, high level. Randomized numerical linear algebra, whether you put the numerical there or not is, I guess, up to you, in a slide. So let me try to give you like a high-level idea of what we've been doing in this area for the past almost 25 years now. Take a very simple problem, approximating matrix products, and one of the simplest matrix products you can approximate A times the transpose, the covariance matrix or whatever you want to call this matrix. So you're trying to approximate a matrix product, and of course you can compute it. It's a problem that has been researched to death. But one potential way to think about this problem is, you know what, I'm not really going to compute the full product. I'm going to pick a few columns from A, put them in C, and instead of computing AA transpose, I'm going to approximate it by CC transpose. And now, if you think about it, I'm going to put some dimensions here, m by n, m by n. Let's say you only pick like S columns. So you end up with, so this should be, sorry, n by m, because it's the transpose. So you're going to end up with m by C columns here, if you pick C columns. This is going to be C by m. So you're getting the dimensions right. So it still works. CC transpose is actually an approximation to AA transpose. And it turns out that under very natural assumptions, since a lot of people care about statistics, under very natural assumptions on the sampling probabilities, how you select the columns of A, the expectation of CC transpose is actually AA transpose. And you can do all kinds of more complicated analysis, but this one is something that, you know, in a randomized algorithms class, I typically ask my students to prove in the first few lectures. And this is something that follows from very basic properties of expectation, essentially. So it's really simple, really nice just to remind people how to do some basic expectation. So you sample rows, columns, or perhaps elements of the matrix. In randomized linear algebra, that's what we do. We basically don't work with a full matrix. We work with a smaller piece of the matrix. You sample rows, you can sample columns, you can sample elements, and you construct new, smaller, perhaps sparser matrices that are close to the original matrix with respect to some matrix norm. In particular, you could get something like AA transpose minus CC transpose. You can bound some norm of this by some upper bound here. I think there is something in the chat. Ah, okay, great. Thank you. So, and I'm happy to answer questions during the talk, so feel free to interrupt me if you want. So essentially, what we are doing is we construct those new smaller or sparser matrices that are close with respect to the original matrix, with respect to some matrix norm, with high probability. Because in most of what we do, we're going to do some sampling, maybe some sketchiness I will talk about later. There will be some randomness. So you're going to have some failure probability there. And this is the sketching part, and this is something we realized much later. So when we started in this area 25 years ago, in the late 1990s, it was all about sampling rows, columns, and elements. And then in the mid-2000s, in 2006, 2007, people realized that another way to create these smaller matrices is to take your matrix A, for example, and post-multiply by, let's say, an n by c Gaussian matrix. And I don't want you to be worried about this Gaussian matrix. Think of it as just a matrix whose entries are normal 0, 1 random variables. You don't even need to normalize or anything, independent from each other. So very, very simple stuff. And notice that this AG is a matrix that is now M by C. So it's a smaller matrix. And you can use that sketch to approximate matrix multiplication and many other things. What's the difference between the two methods? When do you sample rows, columns, elements? When do you sketch? It depends on the application. If you want interpretability, in many cases, it's better to sample rows, columns, elements, because you are keeping your original matrix. You are keeping pieces of your original matrix, and maybe those are interpretable. If you only care about running times, it's typically better to sketch. One big difference is that if you want to sample rows, columns, elements, and get good results, like really good results, relative error approximations, things like that, you need to do careful things. You cannot sample uniformly at random and things like that. You need more elaborate sampling probabilities. Some of you might have heard of things like the leverage scores, the ridge leverage scores, Lewis weights. So these are the sampling probabilities you need to construct, basically. And there are even element-wise notions of some of these sampling probabilities. So if you decide to keep rows, columns, elements from the matrix, you need to do it carefully if you want really good error bounds. If you want to do sketches that basically are similar to compressed sensing, you post-multiply your matrix by random Gaussian vectors, sub-Gaussians work, sparse vectors, the count-mean sketch, lots of things work. Then you can get away with basically not being very careful on your construction. Sometimes people like to call these random projection type matrices that we use for sketching oblivious sketching matrices. They don't need to look at the input matrix at all. Once you have your sketch, you apply matrix perturbation theory. In some sense, this is the other area that you really need to master if you want to get into the randomized numerical linear algebra literature. So you need probability theory. You also need matrix perturbation theory. Why? Because if you get bounds like this for the matrix minus the sketch or, matrix products, things like that, they also imply bounds for the singular values of this matrix versus this matrix. You can use the singular values of the sketch to approximate the singular values of the original matrix. And similar stuff you can do for the eigenspaces, the singular vector spaces, and so on and so forth. And that's where matrix perturbation theory comes into play. It allows you to compare singular values, singular vectors of the sketched versus the original matrix when you do these sketching procedures, either sampling or actual sketch. So kind of in a slide, I wanted to sort of highlight these two things: the randomized algorithms where you do the sampling or the sketching, and then the more deterministic part, if you will, the matrix analysis, the matrix perturbation theory part, which tells you, you know what, the sketch is probably good enough, subject to certain conditions, you're getting good approximations to, let's say, the spectrum of the original matrix. The area is interdisciplinary, and 15, 20 years ago, it was kind of a big deal because, to be honest, numerical linear algebra people and theoretical computer science people were not talking at all to each other. Over the past couple of decades, 15 years, there are many, many workshops, conferences, and places where actually the two groups now come together. So a lot of people now have background on both sides. It used to be the case that in theoretical computer science, numerical linear algebra was not a big deal in the late 1990s, but now it has become quite a big deal. You need to understand notions from randomized and approximation algorithms at the very least from theoretical computer science. You need to know matrix computations, things like the Jean Golub, Charlie Van Loan book, and some perturbation theory. Excellent references there are Pete Stewart's book or Rahendra Bhatia's book on perturbation theory. And more, especially over the past decade, and actually one of the leaders in this area is going to be speaking in this seminar in a few weeks, probability theory, measure concentration for sums of random matrices. And again, realizing that it's the end of the semester, let me expand a little bit on this. So kind of important results in probability theory, right? You want to estimate the sum of the xi's by, let's say, sampling, right? And you have a lot of fundamental results there that tell you how a sum of random variables behaves, not just in expectation, but also asymptotically. For example, you know that one way to estimate this sum is by subsampling. So you can do t equal 1 to s. So you have the sum from I equal 1 to n. You do it only up to from t equal 1 to s, and you pick xit in some way. And you want to basically bound this difference. In expectation, you need to rescale a little bit here. So I should be a little bit careful here. Let me rescale by the probability of sampling. So if you sample a particular element with a certain probability and you rescale by 1 over that probability, you're going to get an unbiased estimator. But of course, kind of the ballpark, the real game, kind of the ball game is to understand the behavior of this difference in absolute value. And that's where you get measured concentration results when your variables are real numbers. What if your variables are random matrices? So there is this beautiful area now of matrix Chernoff, matrix Hefting, matrix Bernstein inequalities, matrix martingales. All the traditional work that has been done for sums of random variables has now been done also for sums of random matrices. And Joel Trop will be talking at your seminar, and I suspect he's going to be covering some of these ideas there. He has one of the defining monographs, if you will, for this area. So I should say that the area did not just do theory, so this is the more theory side between theoretical computer science and applied math. It also worked quite a bit on applications, and there are a lot of applications of some of these ideas of sketching in machine learning, bioinformatics, in data mining, information retrieval, even in deep neural networks. Okay, this is something that I kind of enjoy. So this happened last year. I still saw it, and this might be one of the last talks where I'm going to show this. So we actually made it, randomized numerical linear algebra, made it in the movies. So the Lincoln Lawyer came out last year. It's a TV series in Netflix. It's based on a book by Mike Connelly. There was actually a movie before that that I really liked. This series I didn't particularly like, but friends pointed me out that in season 1, episode 3, this happened. Do something, and he did something. He got her out. In the series they did not show the defense, but at least we know that they mentioned later that she did get her PhD. So it was interesting to see this term, because this is a term that Michael Mahoney and I actually coined like back in 2011, 2012, and it's interesting to see that somehow it made it into a Netflix series. So highlights. That's the main highlight, I would guess. But in terms of more highlights for the past 20 years, what did we do from a more mathematical perspective, if you will? I think that kind of the two big wins for randomized numerical linear algebra were randomized numerical linear algebra approaches for regression problems, and then for matrix decompositions. The SVD and principal components analysis in particular. And both problems are important. They are fundamental in data science. They span multiple disciplines, and they've been around for a while. Regression is really invented, if you will, by Gauss and Legendre back in the 1800s, when they were trying to measure the trajectory of asteroids. Then matrix decompositions like principal components analysis are going back to the time of Hotelling and Pearson in the early 1900s. and they've been used everywhere. So you move outside computer science, you talk to biologists, chemists, economists, engineers, they all know about regression, and many, many people know about principal components analysis as well. What did RandNLA contribute? Well, faster randomized approximation algorithms for the above problems. And it also contributed, I should say, novel methods. I'm not going to talk too much about this, to identify significant rows, columns, elements of matrices involved in regression and principal components analysis. So in some sense, identify the pieces of the matrix that are most influential. And this is where leverage, ridge leverage scores, Lewis weights come into play. There is also a notion of volume sampling, if you've seen it. Recently, well, not recently, it's been 3 years now, there are quantum-inspired algorithms now from randomized numerical linear algebra as well. So some of the ideas that appeared there are also useful in quantum computing. It also identified one of the things, especially in the early days, it was particularly important to decouple the randomized part from the deterministic part. Traditional numerical linear algebra cares a lot about high-quality approximations. The error has to be 10 to the minus 10, 10 to the minus 15, machine precision, as we call it. So it was important in the early days, especially, to understand which part of randomized numerical linear algebra could achieve machine precision, perhaps, and which part could not. And I'll come back to this in a little bit. Lessons that we learned. So I'm going to take 5 minutes or so to talk about some of the lessons we learned over the past 20 plus years at this point. First of all, sketching works. That's the kind of, very high level view of the area. Sketching works in theory and in practice. And by sketching, I include sampling here as well. So if you have a massive matrix, you can deal with it. Sampling the matrix carefully if you can, but if you can't, don't do it carefully. It is what it is. You will get something out of this. Or if you can sketch, even better, perhaps. So if you can multiply by some random Gaussians and work on the smaller matrix, do it. So in problems that involve matrices, using a sketch instead of the original matrix returns good results empirically very often, and provably accurate results. Again, that's a little bit more challenging, perhaps, depending on the particular application. The sketch can be rows, columns, elements. It can be random Gaussian matrices. You can read David Woodruff's monograph on sketching numerical linear algebra to see a lot of details on sketching. It's still an active area. We still come up with better upper and lower bounds for sketching for specific applications. Lesson number 2. Using matrix sketches in downstream applications is not trivial. So it's one thing to say, I'm going to sketch the matrix, but then how are you going to use the sketch? Are you going to use it to do regression? Are you going to use it to do low-rank approximation, clustering maybe, SVMs, interior point methods, which we'll talk about a little bit today, other optimization algorithms, maybe convex optimization or deep learning or something? How you're going to use the sketch is actually non-trivial. How the error propagates is non-trivial. So there is a lot of interest in understanding applications, downstream applications, where sketching is actually used. The sketches can be used as a proxy of the matrix in the original problem. It's the sketch and solve approach. So you sketch the matrix and you do something with the sketch. You never go back to the original matrix. A much better idea is to use the sketch as, I'm going to say, a preconditioner, or to compute a starting point for an iterative process. And if you don't know exactly what that is, all I'm saying here is that use the sketch, compute something with the sketch, then go back and compute more things using the original matrix. If you don't have access to the original matrix, of course, there is nothing you can do. But if you have access to the original matrix, it's always beneficial to iterate. Do something with the sketch, iterate with the original matrix. Specific examples, iterative methods for regression problems using the sketch as a preconditioner. This was done by Chaim Avron and Sivan Toledo about 10, 12 years ago at this point. The blend and pick solver, and there have been many, many solvers inspired by that. It's even part of MATLAB. To compute a seed vector, perhaps in subspace iteration to approximate singular vectors and singular values of a matrix, or to compute a block ReL of subspace. And these two ideas, using preconditioners for solving regression problems or systems of linear equations, or using iterative methods, whether they are subspace iteration or more involved methods using the ReL of subspace, they're not new in numerical linear algebra. They've been around for 70, 80 years at this point. But the use of randomization to construct the sketch and properly analyze it and understand the downstream behavior of this sketch in iterative methods is groundbreaking. Another lesson that we learned, is that pre or post multiplying, let's say a tall and thin matrix A, in this case n by d, by a random projection matrix X, think random Gaussian matrix or any sub-Gaussian or sparse sketches if you are familiar with those, spreads out the information in the rows of the matrix. So essentially what you do is you can take a matrix A where the information, the important part, if you will, is contained in a few of its rows. If you pre-multiply by this X, which is a random Gaussian n by n, then you essentially make all the rows about equally important. And this has a very precise interpretation. It uniformizes this process, the so-called row leverage scores, and it makes the matrix incoherent, if you're familiar with the notion of incoherence. It basically spreads out information in the matrix. You can do it from the left, you can do it from the right, you can do it from both sides as well. And if you have this particular sketch, selecting a few of its rows uniformly at random, and if you have this, if you have spread out the information in the matrix, then you can select a few rows uniformly at random and you can construct a sketch. The last lesson, again, I think one of your future speakers will talk a lot more about this and more properly. There is a very nice symbiotic relationship between randomized numerical linear algebra and matrix concentration inequalities. Things like Bernstein, Chernoff, martingales, all the things we knew for sums or martingales of random variables, we now have equivalent things for sums of random matrices. And this goes both ways. So because of RandNLA, new inequalities have been devised, and RandNLA has been a heavy consumer, of course, of these matrix concentration results. So it goes, as I said, both ways. And I should say that if I go back literally 20 years, back in 2002, 2003, when we did not have those inequalities, analyzing some of the early algorithms we were devising was really tricky. And then matrix concentration inequalities democratized the field because you don't need to prove them in many cases, you just need to be able to use them. And that's actually considerably simpler. And back in the early days, we had to somehow get around them, which was pretty tricky. Back to lesson 2, because this is what's going to be relevant for the second part of my talk. Lesson 2 has to do with essentially sketch and solve versus sketch to precondition, if you will. Sketch and solve means you take your matrix, you create a sketch somehow, and you use the sketch. You never go back to the original matrix. It has a high success rate. If you're familiar with sampling and even basic Chernoff and Bernstein inequalities, you know that the sample complexity depends on the accuracy inversely polynomial. So if you're looking for a target accuracy epsilon, your sample complexity would be about 1 over epsilon squared. And that's large. In numerical linear algebra, this was the early critique of the whole field. If my epsilon is 10 to the minus 10, 1 over epsilon squared is 10 to the minus 20, and 1 over epsilon squared is 10 to the 20, there are not even any matrices with that many rows. So what are you going to do? How are you going to sample? How are you going to sketch? No iterations, of course. Very fast, deterministic running time. Turns out it's tight. I mean, if you ignore information from your matrix, if you only keep a few rows, that's all you're going to do. You're not going to get 10 to the minus 20, 10 to the minus 10 accuracy. It is what it is. Crude accuracy, Monte Carlo algorithm. And then Avron, who actually I'm borrowing the slide from, said, you know what? If I want high accuracy, I'm going to have to do it the numerical linear algebra way. I'm going to have to go back to my matrix. And if you go back to your matrix and you iterate, you can actually get the error to depend on quantities like, you can get the running time to depend on quantities like log 1 over epsilon. So if epsilon is your target accuracy, now you are logarithmic on 1 over the target accuracy. If the target accuracy is 10 to the minus 10, this is just a 10. So this is something you can absorb. But you have iterations. You need to look at your data more than once. Very high accuracy is possible. Success can be the good solution. So you can actually go back and see, did I succeed or not? It's slower than sketch and solve, and of course it has iterations. So you have to pick your poison basically, and we now understand quite well upper and lower bounds for both families of techniques. I find this to be really important and really interesting because one of the things that in many cases you want to do in applications is to combine what I'm going to call inner and outer iterations. You have iterative sketching-based solvers for regression problems or for standard systems of linear equations. You solve them iteratively using perhaps randomized sketching like Blenderpick with iterative algorithms, such as interior point methods, which is what we're going to talk about, iterative reweighted least squares for whatever, could be generalized linear models, iterative algorithms for things like, let's say, clustering, anything you can think that has an outer iteration where the inner iteration needs to solve a matrix problem, especially regression or systems of linear equations, you can have this outer inner iteration combination. So if you have the outer iteration and the inner iteration, and you only solve the inner iteration, and you only do the solver approximately through the inner iteration, you need to understand how the error propagates. And we'll make that more precise in the context of interior point methods. I'm going to talk a little bit about history, make sure we sort of all are on the same page, and the technical results, I'm just going to show some of the results. Interior point methods, you have things like, let me start with linear programming. Of course, the first solution for linear programming was the simplex method, goes back to the 1940s, 1950s. Then in the early 1970s, the ellipsoid method appears, a much more linear algebraic as opposed to combinatorial approach. So simplex is much more combinatorial, whereas the ellipsoid method is much more linear algebraic. And then the revolution comes at some point in the mid to late 1980s with a work by Karmarkar on interior point methods. And the original papers were fairly complicated. They followed the log barrier function, whatever, but the modern approaches are much closer to, in some sense, the Newton method, where they use the Newton direction, and they have what we call a path-following interior point methods. The last decade has seen actually a revolution again, where in theoretical computer science, there are these stochastic path-following methods. Not clear, I guess, how useful they are in practice, but there is a lot of work by people like Aaron Sidford, Yingli Tat, on stochastic path-following methods. In all approaches, at some point, you have this outer iteration where you follow the path, and you have to solve in each outer iteration a system of linear equations. That's where we're going to introduce the inner iteration. This gives rise to what we're going to call inexact interior point methods. And there is some work there, but it was not extremely useful to us when we started looking at this. Inexact interior point methods refer to a family of methods where you solve the system of linear equations in each iteration approximately, and then you want to understand how this error propagates from one iteration to the next, and whether the whole process will still converge. It's well known by practitioners, by the way, if you talk to people who look at simplex or the Gurobi people, the number of iterations in an interior point method is not the bottleneck. In theoretical computer science and in optimization, the number of iterations is what you try to optimize. The computational cost of solving the linear system in practice is the real issue. Broad classification of interior point methods for linear programming. I think it's useful if you've never taken a course on IPMs, and I'm following more or less, I should say, the book by Steve Wright, who has written kind of the defining book in interior point methods. You have the path following methods, and you have the potential reduction methods. Those are not explored in our work. It would be very nice to explore them because they will take you beyond linear programming. So path following methods are not very useful for convex optimization. Interior point methods based on potential reduction are actually useful beyond linear programming as well. Within linear programming, you have, in the path following methods, you have long step methods. They're kind of not the best theoretically, at least, but in practice, they work pretty well. They explore the central path of the simplex reasonably fast. You have the short step methods. They take short steps. They don't deviate much from the central path. I'll have a picture in a minute. Better in theory, slow in practice, and then you have predictor correct, which really is what you want to do, and pretty much state-of-the-art implementations, to the best of my understanding, I'm not an expert on that, follow some variant of predictor corrector algorithms. They're good in theory, they're good in practice. They can be further divided to feasible and infeasible methods, but I'm not going to get there at all. Whether you start with the feasible or infeasible point, we're going to focus here on feasible methods. We'll assume we can compute an initial feasible point, even though this is not always trivial. In practice, it's relevant, but we're not going to really discuss it here. Standard form of LP, to make sure we're all on the same page, you're trying to minimize the sum of the xi's, those are your unknowns, times weight ci. You can think of C as being all ones if you want, it doesn't really matter, subject to AX equal to B, and X has to be non-negative. So this is the standard LP. This is the primal. I assume most of you know that there is a dual. The associated dual problem introduces a dual variable. I'm going to call it Y. I have all the dimensions down here. I'm not going to overdo it by explaining every single dimension. There in my slides. And then you have the slack variable S as well. So the slack variable is also non-negative. The dual variable does not need to be non-negative. In many cases, we treat those as a pair, and especially when we do path-following interior point methods, we try to solve both problems at the same time. And the reason we do that is because we measure progress by the following. Let me go back here for a second. You measure progress by comparing the current value of C transpose X, the primal objective, with the current value of B transpose Y, the dual objective, because you know that at optimality, those two values are going to be equal, which is great. So you have a target. When those two values become equal, you know you've reached the optimal point. And what do you measure? You measure their difference. And that's how you measure your progress. As this goes down, you are making progress in your interior point method. When it reaches 0 or gets very close to 0, you essentially stop. Lots of definitions here. The only one I want you to sort of take a look at is how you make progress. At every step, this is your current iterate. Remember, you are looking at the primal and the dual problem at the same time, X, Y, and S. At the current iterate plus some step size, this is alpha, times the change. So you compute the direction, the Newton search direction, delta X, delta Y, delta S, and you want to basically make a move towards that direction. And you decide the step size, perhaps adaptively. So that's what you do in primal dual path following interior point methods. And the typical result for the feasible case, you start with the feasible point. For long step methods, after order n log 1 over epsilon iterations, you can guarantee that your duality measure, this residual right here, is less than or equal to epsilon times whatever you started with. So this is the common results. You want this log 1 over epsilon dependency, and you want to get close to the optimal solution. You want to make some progress at every step. Eventually, you make it smaller than epsilon times whatever you started with, and you call that a win, and you stop. In practice, actually, at that point, you might switch to simplex and to actually find the optimal solution. This is a figure from a paper that I don't think contributed so much, perhaps, but on the other hand, it drew some figures that I really, really like for interior point methods. It's actually a nice overview of interior point methods if you want to read it. It's not that I don't think there are many new contributions there. This is your central. This is the polytope, right? So this is this is basically the simplex, the space within which you want to optimize. This is your central path right here. And you're not really staying at the central path at every iteration. You're staying within a neighborhood of the central path. So you iterate, you might start here, then you go here, you go there, keep going all the way until you reach something reasonably close to the optimal. This is mu equals 0, so you reach the optimal. Typically, you want to get epsilon close to the optimal, this epsilon neighborhood. So this is visually, if you will, what the central path sort of does. How do interior point methods work? Well, they need to compute the search direction. So this is the search direction, Newton type method, okay? So you need to compute the search direction, and to compute it, it's well known that you need to solve this system of linear equations, which looks ugly and complicated. Forget about those two parts. Think of them as just being zeros. You could have a primal and a dual residual, so you can incorporate that. But at the end of the day, you have this complicated system, but you can rewrite it fairly easily as the following three equations. I want you to first observe, this is a vector. This is input. These are all known. As a matter of fact, D is a diagonal matrix. D square, I guess, is diagonal matrix whose entries are the primal variables divided by the slack variables. Basically, again, think of it as an input matrix, symmetric, positive, definite, tends to get ill-conditioned and poorly behaved as you approach convergence. So it's an issue. This is a vector. This is another vector. So you are solving a system of linear equations here. Once you have computed delta y, computing the update for the slack and the update for the primal is very easy. It's just matrix, what we call matvex, matrix vector products. So all the work is right here in the normal equations. And that's where we're going to sort of try to do some improvement by using approximate methods. So approximate iterative solvers for the so-called normal equations. I should have mentioned that these have a name. They're called the normal equations. So we want to solve them approximately. And of course, That's what you would do in practice. You would not invoke exact solvers necessarily, even though I think if you look at scikit-learn and scipython, they probably use exact solvers, but that means they're not going to scale well. You want to use some iterative solver like precondition conjugate gradients, for example. And the question is, how do they affect the convergence of long step, both feasible and infeasible? We've done that for IPM, for interior point methods, and then feasible predictor corrector IPMs was kind of the more interesting question. We wanted standard practical solvers, not really exotic stuff. There are some exotic techniques out there, but we wanted to understand how precondition conjugate gradients, precondition steepest descent, precondition Richardson, so kind of the vanilla methods, if you will, to solve a system of linear equations, how do they work in this context? And we're going to do the preconditioning. That's where randomized linear algebra comes by using sketching-based approach. And an additional design choice, and we're going to care about this for feasible path following IPMs, is whether we want the final solution to be feasible or only approximately feasible. And I should highlight that this is a real issue, because if you solve the normal equations approximately, then you're almost certainly going to end up with infeasibilities, and that's going to mess up your proof. And actually, and this happens in practice, not just a theoretical concern. So again, this is the setting in one slide. I realize that this has been recorded, so people can pause and take a closer look here. This is what we really want to solve. This is a system we really want to solve. And we're going to solve this particular system using an approximate method. And that's what happens in a lot of applied papers in the optimization community. People solve the problem using approximate solvers. And an immediate problem is that even assuming a feasible starting point, the minute you have an approximate solution, this does not lead to a feasible update. So all the standard analysis of the convergence of IPMs are out of the book. You need to come up with some new idea there. In particular, just to give you an idea of what happens here, you really need those two things here to be equalities in the traditional analysis. Delta x hat is your update, delta x hat is the approximate update. So you want the update to be times the matrix A to be equal to 0, because that's what guarantees feasibility. Remember that AX is equal to B. So if you have AX plus alpha delta X, that's your update. You'd like, in order to remain feasible, to have that exactly equal to B. So you want A delta X to be equal to 0, basically, so that the second term disappears, right? And this would be very nice, except with an approximate solver, this is not the case. So essentially, this is not going to be equal to B, because A delta X hat is not equal to 0. That throws away feasibility. Your analysis is gone. The standard analyses are gone. What did we think about? So my original thought here, and perhaps that would be one of the take-home messages for the interior point methods, is that if you have an approximate solution to this system of normal equations, this solution is not solving what you wanted to solve, AD square A transpose times delta hat y equal to p. It solves something else. Think of this as another vector. Again, I have a special format for the vector because reviewers sort of wanted it that way, but you can think of this as some vector v hat. It doesn't solve the original system, but it solves some other system. So what if we somehow leverage the fact that it solves another system to correct for the error? So this is the correction vector idea that we had. Let's come up with a vector v so that we can, after we solve the system approximately, we correct the solution so that the new things that we compute, if you compute delta y hat, you also compute delta x hat, you also compute delta s hat. So the approximate update satisfies conditions similar to the ones that we want for the analysis. And we compute the correction vector. Can we compute it fast? It's a good question, and it turns out we can. We thought this was a very cool idea. We also thought it was very novel. It was not that novel. There was actually a paper by O'Neill and Monteiro in 2003 who suggested exactly that, except they could not compute the update fast enough. And randomized linear algebra allowed us to do that. So there are, of course, technical details, but the take-home message I want you to keep is that you are solving a system approximately. You are getting back this delta y hat. You are using it to compute delta hat x and delta x hat and delta s hat. And you want sort of the original inequalities in, let's say, Steve Wright's book to still, the original inequalities in Steve Wright's book to still hold. So you fix them, you force them, you fix your solution to make sure that the equalities hold. And it turns out that you can actually do that. And indeed, again, I'm going to hide the technical details. Again, forget about primal and dual residuals. We corrected both feasible and infeasible interior point methods long step ones. It turns out we can construct a correction vector. If I have time, I might show you the formula at the very end. It's very complicated. It works with probability 1 minus delta, can be constructed in time that is actually quite reasonable. For input matrices that are either tall and thin, your A has to be tall and thin, short and fat, or exact Laurent. In those three cases, we beat traditional approaches. For squarish or square constraint matrices A, we do not beat traditional approaches unless there is special structure, like they correspond to Laplacian or something. And we were able to do that using only mathvex essentially, and using this correction vector, the long step feasible and infeasible IPMs work. I want to show one result here for feasible long step IPMs. You can run order n log 1 over epsilon outer iterations of the IPM solver of the interior point method, and log n inner iterations of a randomized preconditioned conjugate gradients, let's say, solver. So essentially, we are arguing that you can get the same results that you would get for standard long step IPMs using approximate solvers. In particular, in this case, this is for preconditioned conjugate gradient, but it works for other things as well. And you need only log n iterations inside, and things are going to converge, and everything works out. Can be generalized, as I said, to exact low rank matrices. A, the constraint matrix, has to be tall and thin, short and fat, or it can be exact low rank. And again, there is a precise running time here that depends on the sparsity of the input matrix A, plus one of the two dimensions, the small dimension, times a logarithmic factor. Forget about the infeasible. Predictor corrector IPMs in the last 5-6 minutes. I want to talk a little bit about the predictor corrector IPMs. The difference with the standard IPMs is that in every iteration, the predictor corrector IPMs take actually two steps. The first step is the so-called predictor step, which tries to reduce the duality measure, but might hurt centrality. You might veer away, you might go away from the central path. And then you have the corrector step that improves centrality. And it obtains the best of both worlds: practical flexibility of the long step IPMs that I just discussed, but the convergence rate of short step IPMs, which is root n better than the convergence of the long step IPMs. So long step IPMs converge in order n log 1 over epsilon iterations. Short step IPMs converge in order root n log 1 over epsilon iterations. Massive difference in theory, perhaps not so important in practice. So we analyze the prototypical predictor corrector algorithm. There are many predictor corrector algorithms, and I'm not going to say that the analysis carries over easily. I think there is quite a bit of work to be done when you move to other predictor corrector algorithms. So we just analyzed the prototypical one from essentially Wright's book with preconditioned inexact solvers. We had to somehow guarantee that the duality measure after each corrector step of the predictor corrector iteration decreases. This was actually totally broken. We had to follow a very new approach in this case. This is a fairly technical and long paper. If we hadn't done the long step work, I don't think we would be able to do this. Because of our understanding of how long step methods worked, we were able to come up with new inequalities for some approximate version now of the duality measure. So we had to define an approximate duality measure now. Visually, this is what predictor corrector algorithms do. They have two neighborhoods. So there is this neighborhood here that is smaller, and then a more expanded neighborhood. The first step in every iteration greatly decreases the duality measure, but could deviate from the central path. So it could be in this big neighborhood. Whereas the corrector step keeps the duality measure constant, but returns back, if you will. So if you look here, you could be going there, and then that's the predictor step, and then the corrector step could take you back here. And you alternate basically at every step between those two neighborhoods. So you are allowed to go far away in the predictor step, but then you come back in the corrector step. Again, you have to solve a linear system. It's like solving this linear system twice. This is the central, this is the centering parameter, sigma. You solve it once with sigma equals 0, once with sigma equal 1. Again, notice that the updates don't matter. They're just mathvex for the slack and the primal variable. It's only for the dual variable that you have to solve the normal equations. Again, same idea. I will actually skip that. We had structural conditions for inexact predictor corrector. More importantly, I think we again employed the correction vector idea, the idea that you are not solving your original system. You're not solving this equal to 0. This is your original system. Instead, you are solving your original system equal to some error vector here. As long as your error vector has small error, basically order epsilon, we proved that convergence is actually not affected. And this is a general recipe. As long as you can construct a correction vector V any way you want, we gave a way to construct it that has small 2 norm and satisfies this equality, you are good to go. The good properties of the predictor corrector algorithm still work even though you are not solving your system exactly. Everything is exactly feasible. Your intermediate solution, your final solution are exactly feasible even though you are employing approximate solvers. So that was pretty nice. And then V, let me clarify that it's user control. So you define V. We gave a particular recipe for V. Let me tell you that the result is what one would expect. That so I'm only sorry. Okay, no. I'm only focusing on this one. For the modified inexact predictor corrector with a correction vector, you have a PCG solver, a precondition conjugate graded solver that needs order log n over epsilon iterations. Those are the inner iterations. And then root n log 1 over epsilon outer iterations. I have the same epsilons for the solver and for the overall convergence of the interior point method. I could have different epsilons. This just confuses things a little bit more, I guess. And the paper has similar results for preconditioned steepest descent, preconditioned Chebyshev, preconditioned Richardson, all those things. I'm going to pass on the technical details. So instead of covering some of the technical details, I decided to talk a little bit at a higher level for randomized linear algebra. I do want to show one thing here. As I said, this is the condition that we had, plus the fact that you want the norm of V, the 2 norm of V to be less than or equal to epsilon. This is the system you are solving. You are not solving it exactly. You are not solving inequality, this equal to 0, if you will. You are saying, okay, this is going to be equal to some error vector. And you need to somehow construct this vector V. So you control it. It's user control. Its 2 norm has to be less than or equal to epsilon, but you need to construct it. You need to know it because you use it. This is our formula for V, and this is not going to make any sense because I haven't introduced much of the terminology. I haven't told you what W is. It's the sketching matrix. I want to show you that it's a long, ugly thing. Again, we would not be able to probably construct this if we hadn't done quite a bit of work over the years on what is called under-constrained regularized regression problems. We used some ideas from those papers, not just ours, other people as well, to construct this correction vector V. Turns out you can construct it efficiently, theoretically. In practice, it's quite expensive. I think there are many other constructions that could be possible that are better in theory, perhaps, more importantly, more relevant and better, especially in practice. But this satisfied all the theoretical properties. This was one of the long papers in ICML last year. And then we had the journal version in JMLR. So, this satisfied all the right properties from a theoretical perspective, especially. Overall running times, they're wrong and ugly. I mean, this is the running time that you actually get here. It depends only on parameters of the original matrix, so it does not depend at all on things like condition numbers and some of the other things that sometimes appear in interior point method. Open problems. We did feasible predictor corrector IPMs that start basically at a feasible point. What if you start with an infeasible point? There is an analysis for exact predictor corrector IPMs that start with an infeasible point by Young and Yamashita. And this is actually a pretty recent result. I thought this would have been resolved a long time ago, but it had not. So this is a paper from 2018. We have a structural condition, this thing that the 2 norm of V of the correction vector is less than or equal to epsilon, and then it has to satisfy an equality. Is that necessary? I mean, we know it's sufficient, but is it necessary? Are there simpler conditions? Are there alternative conditions? I think this is the more important, especially in practice. Do we can the structural conditions change from one iteration to the next? At this point, at every iteration, I'm essentially assuming the same error. There is no reason to do that. Experimentally, actually, we saw that early on, in the early iterations, you need more accuracy than later on. So in the early iterations, you need to be accurate. You need to follow the central path fairly closely, if you will. Whereas in later iterations, you deviate a little bit, it doesn't matter. I mean, the algorithm will fix itself. I don't know how to characterize this phenomenon theoretically. I don't know even if it's a real phenomenon. We observed it on just a few experiments. But understanding iterative processes where the error changes from one iteration to the next, I think would be pretty nice. Lots of results in the theoretical computer science community that we have not really connected to. So there is a lot of work on what I call the stochastic path following method. One of the starting points is a paper by Dan Spielman and his student Deitch back in 2008, that they analyzed a very simple, similar algorithm to what we had without a correction vector, and they return an approximately feasible solution, but it's actually an analysis for a short step approximate path following IPM. And again, I feel that this whole area, we just came up with a simple idea. Can we correct? Is that allowing better analysis? I'm pretty sure that there are many similar ideas that people have not explored there. It's an alternative view to the standard, very well studied interior point methods for linear programming, and we've done absolutely nothing beyond linear programming. So it'd be very nice to go to convex optimization, even quadratic programming, even restricted classes of convex optimization. Papers that I covered here, the first 4 papers, I sort of talked a little bit about them. And then if you care more about randomized linear algebra and you want to read reviews, these are starting points. There are actually another half a dozen, probably very nice reviews out there. So I'm just going to mention those few. Thank you very much for your attention. Let me leave 7-8 minutes for questions.